One more thing we're going to look at today is binomial experiments and binomial distributions. For this game, we're going to look at a spinner that's 1/4 blue and 3/4 red. And this time we're not playing a game where we're winning or losing. In this case, we're just going to repeat this procedure 5 times and record how many times the spinner lands on blue. The first thing we need to think about is if we were going to create a probability distribution for this, what do we want the X to stand for? And in this one, if we're recording how many times the spinner lands on blue, and we're doing this 5 times, then what our X would stand for is how many times out of the 5 we get a blue. So this would be the number of times the spinner lands on blue out of our 5 times that we spun it. If we're doing this 5 times and we want to know how many times the spinner lands on blue, let's think about all the possibilities. It could land on blue no times. So I'm going to write this as a set. These are all of our outcomes. It could land on blue 1 time out of the 5, or 2 times, or 3 times, or 4 times. Or it could land on blue every time, which would be 5. These are all of our possible outcomes for X. These are all of our possible values. If we're trying to write a probability distribution down, those would be the values that would go in our outcomes column, or our column for our random variable X. The next thing we want to think about is whether this would qualify as a binomial experiment, and why or why not. Binomial experiments are a very specific kind of probability experiment. There are 4 conditions that have to be met for something to be a binomial experiment. The first one, and usually the easiest one to figure out, is that there have to be only 2 outcomes. A lot of times when we're talking about binomial experiments, we call these just success and failure. So we have to have 2 outcomes that are complements of each other. So either you get something or you don't get something. In this case, we're only looking at whether it landed on blue or not. So we have our 2 outcomes, which would be blue and not blue. We don't even really care what the other color is, just that it's not blue. So that condition is met. Another condition is that the probability of success on each trial has to be the same. The probability of success then has to be something that we can figure out, has to be something that we would know, and it has to be the same for each trial. So the results of one trial can't affect the next trial. And this we can assume that our spinner is fair, that it's not going to get tired or anything as we do more and more trials. And if we look at how much of our spinner is blue, we can figure out the probability of getting a blue for each particular spin. Here, when we're talking about the probability of success, we're talking about per spin or per repeat of the experiment. That's why we say it's for each trial. Since our spinner is 1/4 blue, that means our probability of success is 1/4. And that in binomial probabilities, we use a lowercase p to stand for the probability of success. Another condition is that we have to have a fixed number of trials. So we have to know ahead of time how many times we're going to repeat the procedure. And in this one we said that we're going to repeat it 5 times. And for this we use n to stand for the number of trials. So that condition is met. And the last one kind of goes along with the second one that I have listed here. The trials must be independent. We already said that the outcome of one trial can't affect the outcome of any other trials. So in this one, each time we spin the spinner, it's going to be a different thing. The way it ends up one time won't affect the way it ends up the next time. That's what we have to assume here for this to be a binomial experiment. So we can assume here that the trials are independent. These are the 4 conditions, and this meets all of those. So that means that yes, it would qualify as a binomial experiment because all 4 conditions are met. Now the next question is how we would find the probabilities for this probability distribution. This is one reason it's important to figure out in the first place that it qualifies as a binomial experiment, because if it does, then we can use the binomial probability calculators or functions on our calculator or on StatCrunch to calculate these probabilities. There is a formula for this, but we're not going to learn it. It's more complicated to learn the formula and understand how to use it than it is to pull out your calculator and use the function there, or to pull up StatCrunch and use the function there. So I'm going to show you in StatCrunch how we would do this. So in StatCrunch, I just have a blank data editor open, and I'm going to Stat Calculators and Binomial. For this, we need to put in the number of trials, which is the n, so that's 5, and then our p, the probability of success on each trial, which is 0.25. To fill in this table, we want to use an equals here. For this first one, I'm going to put in x equals 0 because I just want the probability of getting exactly 0 blues. That probability, rounding it to 4 decimal places, would be 0.2373. And if I wanted to write this out in words, this would be the probability of exactly 0. So our probability of getting exactly 0 blues would be this. And then we could fill it in for the rest of these just by changing our number over here. So for 1, and again, this is the probability of exactly 1 blue out of our 5 spins, would be 0.3955, and so on. There are probabilities for each of those outcomes. We could check this by adding these up, and we should get something really close to 1. It might be just a little bit off if there's enough rounding error, but it should be really close to 1. Notice the one that has the highest probability here is getting exactly 1 blue. And if you look at this, they do a little probability histogram for you in StatCrunch, and it even shows what those probabilities are. The reason this is skewed to the right so that these are higher on the left side is because our probability of success on each trial is only 0.25. That means our probability of success is less for the higher values, it's more for the smaller values. Now, if we want to find the mean of this probability distribution, since we've got these probabilities, we can go through and multiply all these and get our probabilities that way. And I'm going to show this, but this is really not the easiest way to do this. If you have a binomial distribution, then actually finding the mean is really easy. All you have to do is take the number of trials, which in this case is 5, and multiply that times the probability of success on each trial. And that's going to give you your expected value, or your mean for the distribution. So the mean here is going to turn out to be 1.25. And I could have gotten that by going ahead and multiplying all these and adding them up, but I didn't have to for this. All I had to do for this was take the n and multiply times the p. This is one of the easiest formulas that you'll see in this class this semester, is for the mean of a binomial probability. So the easy way to find this is to use this formula. For the mean, it's just n times p. Now another thing we could do with this is find the standard deviation. The reason we would want to find the standard deviation for a probability distribution is that then we can do things like look at the mean plus or minus 1 standard deviation, or the mean plus or minus 2 standard deviations. We can talk about it with the empirical rule that we talked about in the last unit. But to do the standard deviation for a table like this, We really don't want to do that by hand. This is another one that has a super easy formula. If it's a binomial distribution, then the standard deviation is equal to the square root of n times p times 1 minus p. So this is another really easy formula to find the standard deviation. For this, we would take our 5 times our p, which was 0.25, times 1 minus p. We could take that and plug the whole thing in our calculator, and that would give us the standard deviation. Now, one thing about means and standard deviations, when we talked about these kind of statistics in the past, we had that rule of thumb for rounding these, and that said that you want to go 1 decimal place further than the values you have in your data. In this, if we look at our outcomes here, these are all whole numbers, so that means technically for our mean we would want to round that to 1 decimal place, which would give us actually 1.3. And for the standard deviation, if we round that to 1 decimal place, that would give us actually 1.0. This is another place when you're doing your homework from my stat lab. Read the directions carefully because it will tell you how many decimal places it wants you to round to. There might be some problems where they don't necessarily follow this rule of thumb, so just pay attention to the directions for those. Let's talk about one more thing with this binomial distribution. We already found the probabilities for landing on blue exactly 0 times, exactly once, exactly twice, and so on. If we want to find the probability of landing on blue less than 2 times, the important thing here is to figure out which of those outcomes this would include. So if we look at all of our outcomes, it was 0, 1, 2, 3, 4, and 5. Those are all the outcomes in our sample space. We need to figure out for this one exactly which of those outcomes would be included if we're saying less than 2. Less than means it doesn't actually include that number. So less than 2 out of these outcomes would just be 0 and 1. That means we're trying to find the probability of landing on blue 0 times or 1 time. There's the table that we already had, so we could just take the probability of exactly 0 and the probability of exactly 1 and add those together, which would give us 0.6328. Now if we were going to write this in inequality notation, this would be the probability that x is less than 2. Now let's look at the probability of landing on blue at least 4 times. Again, we want to figure out which of those outcomes are included in this. At least 4 means we're including the 4 and anything greater than that. So that would include the 4 and the 5. Again, since we've just got those 2 outcomes, we could calculate those 2 and just add them together. The 0.0146 plus the 0.0010, plus the 0.0010, which would give us 0.0156. Now to write this out, this would be the probability that x is greater than or equal to 4. So the wording makes a lot of difference in these. How about the probability of landing on blue every time? Out of the 5 trials, if we land on blue every time, that means the only one of these outcomes we're looking at is just the 5. We already have the probability for getting exactly 5 blues, and that is that last one in the table. So the probability of x equals 5 is 0.0010. Here's another one with at least. The probability of landing on blue at least once. This would include the outcomes 1, 2, 3, 4, and 5. At least once means we're including the 1, and we're also including anything greater than that. So this includes everything except for the 0. The reason this says use the complement is that if we were calculating all these from scratch, if we didn't have these already, it'd be a lot easier to just calculate the 0 and subtract that from 1. 0 would be the complement of at least 1. So what we would do here is we would take 1 minus the probability of x equals 0. And even with our table, this would be a little bit easier to do, because then all we have to do is take 1 and subtract that one probability. This is a hard thing to remember, but it's important that the complement of at least 1 is 0. When you're dealing with the binomial probabilities, your outcomes always start at 0 and they go up to whatever your n is, to your number of trials. Anytime you're trying to find the probability of at least 1, it's easier to find the probability of exactly 0 and just subtract that from 1. Now, one last problem. Let's find the probability of landing on blue more than once. We have to figure out which outcomes this would include. More than once means we're not including the 1 this time. This is going to start with the outcome of 2 and go up. For this one, we could take those 4 from the table and add them up, or we could even use the complement for this one. So the complement would be anything else in our set of outcomes up here that's not included. That would be 0 and 1. So we could do this. We could take 1 and subtract the probability of the 0 and the 1 added together. And if we look back here, actually we already did this one. We found the probability of 0 or 1, which was 0.6328. So if we already had figured that out, we could even use that and make this even more of a shortcut. We should get the same thing as if we added up the probabilities for 2, 3, 4, and 5 as if we do this with the complement.